Hey everyone, thanks for your attention. The paper we reviewed is Learning Fast Approximations of Sparse Coding. The authors are Karol Gregor, Yann LeCun, and in our group we have Xinyue Hu, Sam Gosh, Jerry Kong, Yehu Chen, and Terry Ma. Okay, first let's talk about the basic definition of sparse coding. Its acronym is SC. Sparse coding is a method to finding out over-complete sparse basis vectors and conduct linear combination to reconstruct input vectors. We have a dictionary matrix WD. The size of WD is m by m. And we have a cost function EWD of xz. X is the input vector and z is the coding of x. So basically, WD is the projection from the coding space back to the input space. So WD times Z gives us the approximation of input vector x hat. So the cost function consists of a reconstruction error between the x and the x hat plus a L1 norm of Z, which is called the L1 penalty term to brings the sparsity of Z. So go back to the definition. The over-complete means m is larger than n, and sparse means there are many zeros in Z. There are two optimization problems in the process of sparse coding. The first one is in inference pass, which means with given WD, we minimize the EWD of XZ with regard to Z, and we obtain the optimal code Z star. And the second optimization problem is the update of WD. The update is to conduct the minimization for the expectation of EWD over a training set. So all in all, sparse coding is more like extracting high-dimensional abstract features of raw input. It has many applications, such as visual neuroscience, image restoration, and object recognition. The advantage of sparse coding is it can automatically extract meaningful data, which is useful for unsupervised learning. However, sparse coding is a computation-intensive process, so it is slow and it is hard to be applied in real-time applications. For example, in image applications, sparse coding is conducted for every single input patch, and an image is likely to contain many such patches. Like we're gonna conduct sparse coding for this blue patch, and then we conduct again for this orange patch, and then we conduct sparse coding again for this green patch. So that's inefficient. And in this paper, the authors proposed an efficient method to conduct sparse coding. They proposed a learning-based method to compute approximations of optimal sparse codes in a fixed amount of time. They train a parameterized nonlinear encoder function to predict the optimal sparse code. And they proposed a code component computation method, which they called explaining away.
Here, let's talk about the two previous approaches to the sparse coding inference problem. One is iterative shrinkage and thresholding algorithm, ISTA for short. FISTA means fast ISTA, an algorithm quite similar to ISTA. The other one is coordinate descent. First, let's talk about ISTA. If we look at the objective function we have, we can see it as a combination of two terms. And the original paper of ISTA generalized it to a sum of a Lipschitz continuous function and a continuous convex function, meaning that the ISTA can tackle a more general class of problems. And essentially, the ISTA uses gradient descent to solve this problem. First, if we ignore the part of L1 norm restriction, the L2 norm in the blue box is just a quadratic function we're all familiar with and know how to optimize it using gradient descent. And the gradient of it is shown in red box. The line down below is one line in their pseudocode. So in their pseudocode, they let L be greater than the eigenvalue of WD transpose times WD, which is dictionary transpose times dictionary. The algorithm uses 1 over L as a pretty standard step size to update Z until convergence criteria is met. Now we need to understand what this function h is doing, and we need to look back at the original paper to understand it better. In the previous slide, the original paper sees the objective function as a combination of two functions, f and g. We use the gradient descent to minimize f, and we use this function prox to add in the restriction enforced by g. So prox is a trade-off function between gu and the difference between u and x, weighted by 1 over 2 times current step size, meaning that u minimizes gu while remains close to x. With this information, we are now able to understand what the function h does. So when gu is L1 norm in our problem, by taking the derivative of the part in the blue box and analyze positive and negative case separately, we can get to the soft thresholding function down below, which is h we use in this problem. Thus, we can see that ista is basically two alternating steps. First, use gradient to minimize fx, and use a proximity operator to shrink the updated value to ensure L1 restriction is applied. And fista, fast ista, is just adding a momentum term in the updating process, which makes the algorithm both run faster and converges faster. Another method the paper mentioned, coordinate descent, suggested by its name, descend one coordinate at a time. Unlike ista, in which every coordinate is updated in one iteration, coordinate descent pick the one coordinate that changes most rapidly in a iteration as shown in the red box, and update that coordinate according to the similar gradient descent update rule. When the paper was published, coordinate descent was widely acknowledged as the fastest algorithm for this inference problem.
So the goal of trainable sparse code predictors is to design fast encoders that can be trained to compute approximate sparse codes instead of solving the optimization problem at prediction time. There are several properties that is desirable for such encoders. The encoder should be continuous and almost everywhere differentiable with respect to their parameters and with respect to the input. Differentiability with respect to the parameters will ensure that we can use gradient-based learning methods to train the predictors. Differentiability with respect to the inputs will enable their use as components of larger global trainable systems, such as adversarial or generative models. So the paper proposed a nonlinear parametrized feed-forward architecture denoted by z is equal to fe of x w, where w collectively designates all the trainable parameters. The training of the encoder is achieved by a stochastic gradient descent to minimize the loss function Lw, which is the average of individual loss defined as the one half of square distance from the architecture output to the orthogonal sparse code. Here, z star p is the orthogonal code for sample xp and is obtained with the COD method. So the paper here assumes that test input vectors are joined from the same distribution as the training samples. So the whole idea of training the architecture to predict the optimal sparse code makes sense. So the paper considers a simple class of encoder architectures as the baseline. Z is equal to G of WE times X, where WE is the trainable matrix and G is the coordinate-wise nonlinear function. Gx is equal to D times hyperbolic tangent X. Here D is also a trainable diagonal matrix. However, this architecture has two shortcomings. The first shortcoming is that this architecture is difficult to produce code values equal to 0, since hyperbolic tangent is high derivative near 0. Here's the product of the derivative of hyperbolic tangent. As we can see that the derivative has essentially value 1 at the location x equal to 0, which is very high. so this is not desirable for the sparse encoding. The second shortcoming is that the baseline architecture cannot possibly exhibit competition between different subsets of code components, whose corresponding basic functions could reconstruct the input equally well. Intuitively, this means that the architecture cannot distinguish two different sparse encoding W1 and W2 with the same reconstruct error. So consider the example of W1 is not equal to W2, but the loss of W1 XP is equal to loss of W2 XP. So there is no way for this baseline architecture to distinguish W1 from W2 since they have the same loss function. So how to address the first shortcoming? The intuition is, since we are doing sparse encoding, why not shrink the derivative around neighborhood of 0? The proposed solution is to use the similar shrinkage function similar to the one we use in ISTA instead of hyperbolic tangent. So the paper tests three different such shrinkage functions. The first one is the simple shrinkage function f(h theta of x), which has the property of not smooth, not differentiable. The second function is double hyperbolic tangent, gx equal to d times hyperbolic tangent x plus u plus hyperbolic tangent x minus u, which has the nice property of being both smooth and differentiable. The third choice is some learnable parameterization of the nonlinear function, such as mixture of Gaussian IBFs or piecewise linear function. So here is the plot of the nonlinear function we seen in the previous slides. As we can see that the green and brown lines are double hyperbolic tangents and the simple shrinkage function, which looks very similar to each other. The experiments show that the code prediction errors obtained by the trainable nonlinearities are slightly better than the shrinkage function, so the paper decides simply to use the shrinkage function h theta in all the experiment setting. How to address the second shortcoming? The intuition is to allow code components to compete to explain the inputs, which is denoted by the notion of explaining away. The proposed solution is to use feed-forward networks whose structure corresponds to a few steps of ISTA or a fixed number of steps of COD. So previously, Z is equal to G of W times X, where the activations of two code components are independent given the inputs. So this means that conditional on input X, Z1 is independent of Z2. However, now Zk plus 1 is equal to H of We times X plus S of Zk. So conditional independence is broken. Zk could possibly influence Zk plus 1 through S, which is similar to the time unfolded recurrent in the network.
So as we just saw, the naive or baseline encoder works in a way such that only the parameters of the WE matrix are updated depending on some training inputs and their corresponding optimal outputs. And there is no interaction between the sparse code components. But this is unlike the ISTA or COD algorithm, where we saw that either all the components or a single component of the sparse code undergoes changes every iteration. So in this section, two encoders are introduced, which try to merge both the concept of trainable encoder and the concept of interaction between sparse code components. And so basically, so this uses, they use a feed-forward neural network whose structure correspond to a few steps of the ISTA or COD algorithm. The matrices WE, the S, and the vector theta, which can be seen here, are basically not computed, but are rather trained to minimize the encoder loss function, which we saw earlier. And these learning algorithms have been named learning ISTA or learning COD. So as a reminder, this was the update equation for the sparse code of ISTA. And this can be written as this, and again can be written as this one. So this is just to store the intermediate values, and these two equations are basically used for in the learning ISTA forward propagation algorithm. And these two equations are applied some number of times of say time steps t to obtain the sparse code, and the final sparse code obtained is given by the zt. And this algorithm can then be represented by a block diagram as can be seen here, it has been shown for 3 time steps. And all the values that are in red are stored for backpropagation to be changed during that backpropagation procedure. And so learning the parameters of W, E, S, and theta, which are present actually in this W matrix, it is basically done by this particular equation, which is the stochastic gradient equation. And computing this particular gradient, it is done by the backpropagation algorithm. All the values in red, they have been basically saved during the forward propagation algorithm. And the backpropagation is basically is done by starting from the values obtained in the final step T, capital T, and going back to the first time step. The equations that we see here, these exact equations have been obtained using the chain rule. And some of the examples are shown here, example equations. And this particular equation is, if you can see, the derivative of the loss L with respect to ZT is written in this particular way because ZT plus 1 actually depends on ZT. Coming to the second equation, the derivative of loss S derivative of loss L with respect to S is written in this way because S is time shared across the time steps, as we saw in the block diagram earlier. And so since ZT depends on S, so this chain rule applies. And the H prime of theta T is basically a Jacobian of the H with respect to its corresponding output. For example, as seen here. And this is basically a squared and binary diagonal matrix. Now coming to the LCOD forward propagation algorithm, this is basically exactly the same as that of the COD algorithm which we saw earlier, but it's just that it's applied only for T-1 number of steps. And the important thing to note here is in the last line, that is, if the total number of iterations is 0, then we basically obtain the baseline encoder. So what this algorithm says is, if we do it if we increase the number of iterations, then it's only getting better from here. And the backpropagation algorithm for LCOD is essentially, the procedure follows the same as that of the LISTA algorithm. And it basically follows these equations of backpropagation, which are obtained using the chain rule.
Now I will introduce the results. In the previous sessions, we introduced several experiments which compares the performance of different methods on exact sparse code prediction. And the prediction error for LISTA are shown in this table and this figure for varying depths. We see that the higher the depth, the better the prediction error. This table is the prediction error for different non-linearities with baseline encoder. And we can see a single iteration of LISTA reduces the error by almost a factor of 2 over a simple shrinkage encoder. And in this figure, the red color is m equal to 100. The blue color is m equal to 400. For m equal to 100, FISTA need 18 iterations to reach the error of LISTA with 1 iteration. And for m equal to 400, FISTA need 35 iterations. Hence, we can say LISTA is roughly 20 times faster than FISTA. The results for LCOD are shown in this figure. Each iteration of LCOD costs OM operations. So the cost of the initial operation is ONM, and it is remarkable with only 20 iterations, since it only needs to add a teeny additional cost to the initial calculation. So it is much smaller than a single iteration of FISTA or LISTA. And from the figure, we can see in this case, the error is already below 2. And also, it takes 100 iterations of COD to reach the same error as 5 iterations of LCOD. For a larger number of iterations, LCOD loses to COD when the matrices are initialized randomly. In the second set of experiments, we investigated whether the improvement in prediction error leads to a better recognition performance using the MNIST dataset. These two tables are two experiments for the comparison of COD and LCOD. In first experiment, the COD and LCOD methods with code of size 784 were trained on the whole 28 multiple 28 pixel images. In second experiment, the COD and LCOD methods with 256 dimensional codes were trained on 16 multiple 60 pixel. For the performance, while the error rate decreased with the number of iterations for all methods, the error rate of LCOD with 10 iterations is very close to the optimal, and differences in error rates of less than 0.1% are insignificant on MNIST. Now the conclusions. We have shown that learning the filters and the mutual inhibition matrices of truncated versions of FISTA and COD leads to dramatic reduction in the number of iterations to reach a given code prediction error, and roughly by a factor of 20 for a low iteration case. Even if accurate codes are needed, LCOD can be used advantageously to initialize COD, and in the future work, the method will be applied to image restoration and object recognition tasks. That's all. Thank you.